Okay, thank you. Good morning. So I want to talk a little bit about networking in OpenStack. So if you think about cloud networking, I don't know if you know the fable of the six blind wise men, where the six blind wise men are brought to next to an elephant, and they each one of them grabs a piece of the elephant and says, "Well, if I feel the trunk, this thing must be has this sort of characteristics." I mean, cloud networking is a little bit like that, where we heard about Mark Collier this morning talk about OpenStack being an integration platform. Well, integration means bringing in a bunch of different perspectives. And you have, when it comes to networking, you have very wide different perspectives of what cloud networking should provide and what it is and what does it need to do. So you have, if you're talking about networking, you typically have application owners. They have the perspective of wanting to deploy applications. You then have people that are centered, that think about switching. What does switching need to look like? And they have a different, completely different set of expectations of what networking should bring to the table. Then you have wide area networking people, which again have no common language with the switching guys or with the app owners. You have the DevOps teams that typically operate OpenStack, and you have SecOps in many companies. And then you have people like myself, which are software implementers. And, an integration platform has to bring together all these different perspectives and get something working that satisfies all these different siloed views. So let's look about what a cloud application looks like from the perspective of somebody that wants to deploy an application. A standard application looks like a little bit what you guys see in that slide over there. You have the outside world where the clients exist, whether the outside world is inside the corporate VPN or the public internet. That the architecture is pretty much the same. Typically, you're coming in through a load balancer. You hit the front-end servers. The front-end servers then talk to multiple tiers. Some of those tiers can be owned by the same owners that own the application. Some of them can be consumed as a service. So, for instance, it's very common that databases are operated for multiple different applications. And then you have a set of services that are common to every application. You need jump hosts, you need log servers, you need management servers. So from the perspective of an application owner, this is what networking is. And what I want to do is press a button, define the application, and just push it to the cloud. So if you talk with application developers, for them networks are RPC sockets between layers, and they care about access control, who can talk to whom, and latency and throughput. And from a perspective of infrastructure as a service, an application owner wants to be able to have a deployment template. Typically in OpenStack world, this is a heat stack, and they want to be able to code review that application deployment template, deploy it to production, and that's it. As an RPC layer, the expectation is that the cloud networking solution provides stable endpoints. So very often, when you deploy an application stack, you need to be able to inject either IP addresses or DNS addresses into the configuration files of that application stack. And several configurations, for instance, are done still in terms of IP addresses, even because DNS is not always a reliable way to resolve addresses in the cloud. So there's an expectation that those IP addresses are stable even if your workloads move around in the cloud. So if your workload gets killed in server A and shows up in server B, the IP address has to be constant. And there's also the expectation of load balancing between an external network front end and the application tiers. So that's pretty much the problem statement from the perspective of the teams that own an application and want to deploy it. The guys that own the cloud infrastructure have a completely different perspective of what networking should be. So, if you step back from an infrastructure perspective, what is a cloud? A cloud is an infrastructure which has probably a high fixed cost of setting it up, has a high engineering cost, but then has very low incremental cost of adding workloads, right? The idea here of a cloud is that you can deploy a new workload and it costs you cents to the dollar because you automated everything up front. So what are the costs? What's supposed to be the costs on a per workload base? They're supposed to be dominated by power, the power that the servers consume, and the cost of those servers themselves. So the way to run a cloud at scale is by increasing the utilization of your servers. So when it comes to networking, the perspective of cloud infrastructure is that network should never be a bottleneck because your cost is dominated by servers and the power they consume. So you want to make sure that you can drive, typically the bottleneck in server utilization is memory utilization. So that's what you're trying to maximize. And from the point of view of running an infrastructure, the networking is supposed to never prevent you from deploying the workload that would otherwise fit there in that server. So if you're trying to build this physical infrastructure, the goal here is that you can have any workload anywhere, and then minimize the cost per port. The any workload anywhere perspective makes you design a network where there shouldn't be any oversubscription on the fabric. Typically, you have two 10 gig ports or two 40 gig ports on a per server basis, and then once you hit the top of rack switch, you just have zero oversubscription versus traditional IT designs, which would have sometimes 10 to 1 or 20 to 1 oversubscription on the infrastructure. To get to that design, you need a layer 3 fabric design beyond a reasonable scale. So once you go beyond a couple of racks of servers, you need your fabric to be able to have a layer 3 only design and run as much as possible as a closed network. The other requirement is that from managing the infrastructure, it doesn't really work for the workloads to be changing the configuration of the infrastructure. So the network layer, the fabric layer, needs to be a relatively static configuration, independent of what the workloads are doing. So if you think about it, this view of what networking needs to provide is completely at odds with what we talked before of what is the view of networking from the application owner. If you think about the wide area network teams that exist on any large content provider or service provider, their perspective of cloud networking is not the switching infrastructure. What they care about is that you can connect networks that exist in two different availability zones, two different locations, and they can, for instance, do anycast, route the same IP address to the point where the network is available. So for the wide area networking teams in a content provider, for them, cloud networking means go to any cloud that is available. Again, it's a very different perspective than the other silos we've talked about. So you have a different set of teams, which are sort of what I call the cluster operation teams or DevOps teams in any cloud provider, which essentially are looking at the problem from the point of view of managing software. These guys need to be able to deploy releases of code and releases of capability by managing software. It's, if you give them a solution that's tied to any hardware, that would be an issue for these teams typically. They need to have programmatic APIs to provision just about anything, and they care about high availability. So one of the things they're typically asked to do is ensure that they can test the failure of every single component, and for every single component, the service still has to be operational. Most of the cloud ops teams, their day-to-day job is to develop tools to monitor the cluster and make sure that the software is running. So, again, very different perspective of what networking needs to bring to the table. SecOps, most content providers will have a dedicated security team, and these guys' job is to make sure that all access is authorized, and that they can deploy policies that are consumable by the app owners. So it's two things. We talked about, for instance, having a database service that is consumable by multiple applications. So that's the typical kind of service that needs to have very strict access controls to prevent data leaking. And not only there need to be access controls, but a lot of content providers need to make sure that they pass a given set of certifications. So they need to be able to audit all the accesses that exist on that infrastructure. Finally, when you talk about people that write cloud software, you have also the implementers, and you have, when it comes to networking, two very different perspectives. People that come from sort of the web side of software development that tend to focus on seeing networks as VLANs, and they look at developing networking as putting together a bunch of different components that already exist. So, using RabbitMQ plus MySQL in order to distribute networking state, and reusing OVS and IP tables. And you have a different set of people that come from a much more embedded systems background, and they think of networking as a custom forwarding engine using a custom message bus. So when you think about OpenStack networking, and again taking the sense that OpenStack is an integration platform, you need a solution that somehow talks to all these different people. And most of the times the problem that we face is actually having a common language with all these different perspectives. So what we try to do in OpenContrail is to actually build a standards-based cloud networking solution targeting what we perceive as the requirements of a large-scale cluster. Typically the requirements we see from an application perspective is the ability to use the standard Neutron API in order to define load balancers, ports, and associate different objects with each other. So how does OpenContrail implement the, suppose you have an application owner has an e-template that defines this topology. We translate that in OpenContrail by converting the calls to the Neutron plugin instead of calls to the Contrail configuration API. And so each of the neutron objects gets mapped into a control API object that is then stored into a graph database. And there's a couple of important points that happen here. One of them is that when you use OpenContrail, we don't use the Neutron database, the native Neutron database. We use only the Contrail API database. And the second interesting point that happens here is that by storing all the Neutron objects in a configuration API, we implicitly have a mechanism to figure out which configuration is relevant where. So take the problem of security groups. Security groups need to be known in all the compute nodes which have a VM that uses that security group. So using a graph database, we build a general purpose mechanism that allows us to say, well, if a compute node is associated with this node in the graph, a VM, then I can do a breadth first search based on that VM and figure out what are all the objects that are relevant to that compute node, and we use that mechanism to figure out, who knows to know about security groups or every other object that's relevant to that VM. So there's, from a configuration perspective, a general purpose mechanism that allows us to figure out what configuration is necessary anywhere. If you compare to, say, the default Neutron implementation, which treats every single application as a different silo, where security groups are handled by a piece of code, DHCP is handled by a different piece of code, etc., etc. So that's kind of one of the ways that we translate the problem very differently than you see in the default Neutron implementation. From the perspective of a compute node, OpenContrail has two components that get installed in the compute node. It has a user space agent called a vRouter agent, and a kernel module that implements the data plane for virtual machines or containers also. And as we've seen before, the configuration is then pushed down to the agent according to a generic mechanism. From a forwarding perspective, what happens is that each virtual NIC, also called a Neutron port, gets associated with an explicit routing table, a self-contained routing table, which we call a VRF, because that's the term that comes from a technology we utilize. You can think of this as a private IP routing table associated to each Neutron port. And each compute node, when a VM is instantiated, advertises the IP address that is associated with a Neutron port, IP addresses, because you can have multiple IP addresses associated with a Neutron port, and you can have things like floating IPs that are associated with the port. And from the perspective of this kernel module, we do a couple of simple operations. We do an IP routing lookup for packets that are coming from the virtual machine down to the infrastructure. And on the reverse side, we do an MPLS label lookup that converts an MPLS label on the packet into the incoming interface. It's a very, very simple, conceptually very simple data plane that we package as a kernel module. And from the perspective of a virtual machine, the virtual machine sees a single default router, which is that the hypervisor itself. So it thinks that it has, for instance, a /24, a subnet route, but when it tries to ARP, the ARP reply is given to it locally by that router that is distributed and sits in every single compute node. So still trying to map that initial case of I have a front end talking to a database. If you have two instances, one instance sits in this front end, so web server routing table, and you have a database routing table. The way we connect this in using OpenContrail is by importing the routes of each table when two things have connectivity. So you know, instead of having an implementation where you'd have to go to a common router that sits in a virtual machine, which used to be what the default Neutron implementation tends to do, we route traffic directly from ingress server to egress server simply by knowing which routes are into those different domains. And that decision is just controlled by looking at the forwarding tables. So the routing decision is done in a controller. So the controller knows that you've configured the right Neutron. You went to the Neutron API and created a router object. And when you do that, the controller knows, okay, these routing tables need to have common routes, downloads the routes down to the forwarding table, and the forwarding happens directly from ingress to egress without having to bounce to a point in the middle. Right? Because the standard expectation here is that you spray your workloads across any of the compute nodes that you have without having to localize the workloads that talk together in the same rack or something like that. The way we do that and the way we built this distributed router implementation is based on a technology that's used in the service provider space for over 10 years, which service providers used to implement virtual private networks for large distributed enterprises. And we did that because we know that technology scales to very large numbers of routes and very large distributed systems. So working based on a proven implementation, on a proven design, is something we thought, well, that would be a good starting point. We just took that way of building systems, and we have implemented it in a cloud networking way that you can provision everything based on a REST API. The big advantage of doing that is we get direct interoperability with, for instance, a service provider network that is already using this technology, and also gives us direct interoperability across clusters, because we can extend a network that exists on one cluster with some other cluster based on the same set of common mechanisms. It gives us a way to federate clouds automatically. So typically when you deploy that application, there's an access control. So for every forwarding decision, there's also needs to be an access control policy. In the OpenContrail implementation, the first packet of each flow, the header gets sent to the user space agent. So there's a global flow table for all the flows within a single compute node. The first packet of the flow gets checked against the policies by the vRouter agent. And given that we distribute all the relevant routes everywhere, we also associate with a route the security group ID, of the originating port. So if I go back here, I had my app server information, so which lists all the IP addresses that I have on my front ends. I have the database VRF, which lists all the IP addresses. When I mesh this information together, I also pass in the security group information. So when it's time to do a security group check, the security group ID is known by all the distributed routers. So I don't need to explode security groups to all the IP addresses that could possibly be using that security group. If you use the Neutron API, you know that the security group ID, you can configure a match on security group ID. And if you have to, in some implementations, you have to then take that ID and expand to every single IP address that could be using that ID, which causes you the problem that every time you add or remove an IP address to that security group, you now have to push all this information everywhere. And it's traditionally a way to melt down a network. So, like any other problem in computer science, you can solve it by adding another level of indirection, I guess. So there's a level of indirection here for security groups. Another way we try to meet the requirements of, say, a SecOps group within a content provider is to make sure that we record all the flows that exist in the system. So every single flow record, the same flow records that we use to do the security group policy check, they're sent to an analytics collector, and they're stored in the time series database. So you can come in after the fact and do a query and figure out what were all the accesses to the database network. And that gives you a way to audit the system to ensure that indeed your security policy and the traffic flows, your expectations match what happened in the network. You can also use this time series database to figure out historic information, what sort of traffic did you have, etc. Part of another service that's provided is load balancing as a service using active and standby automatically. So as much as we can, we try to distribute all the implementation of all the components. But in load balancing, you typically have semantics such as load balance persistence by, say, session cookie. So a customer comes from, if a customer connection comes from the outside, if you have a LBAS semantics of session cookie persistence, once you pick one of the backends to send the traffic to, every other request that has the same cookie is supposed to go to the same backend. So that requires you to look inside all the HTTP requests and look at the cookie. That's one of the semantics that are supported by the LBAS API. When we implement that with OpenContrail, one of the things we do is we use an active standby mechanism so that if you have a failure in the active, the standby will immediately take traffic and start doing the load balancing decision. Of course, you would lose you'd lose information about that session cookie binding. So the existing sessions would be affected, but you still can serve new sessions, and you'd have, at the very least, a faster mechanism than if you just have one load balancer VM and that load balancer goes down. That's a significant availability issue. So part of the issue that we have to worry about when we do networking is the networking availability. So if you think back to the problem we're trying to solve, and which typically from a user perspective it looks like this, right? Traffic from the outside hitting a load balancer, going to a set of app servers, and then maybe hitting one or more tiers. From the point of view of the application owner, what they see is a platform that provides the networking semantics of Neutron, and it does so, giving them things like high availability for the services that the networking provides, whether it's load balancer or source NAT. There's an implicit high availability implementation, so the application owner doesn't have to worry about failures in that layer. They also see a platform that implicitly provides them federation, so you can have a private cloud managed by one entity, and that can federate at the networking layer with a say a public cloud or a private cloud managed by a different entity, because there's a mechanism built in to exchange routing information between different entities. And pretty much that's what the standards-based approach buys you, is a mechanism where two different entities could federate. From a point of view of the cluster operations group within a service provider, OpenContrail is a distributed router that is provided as a software only. And if you think about it, web servers don't tend to talk much to each other. At the very least, sometimes there's a discovery mechanism, but within a tier, you don't tend to see a whole lot of traffic within that same tier. So thinking of networking as VLANs kind of fails to take into account that the traffic patterns are mostly bouncing traffic between different tiers. So from a performance and latency perspective, you really need a networking solution that's based on a distributed router implementation rather than based on the concept of a VLAN or VXLAN. From the point of view of, again, the DevOps teams, the other thing that OpenContrail brings to the table is a distributed implementation of most of the services. So DHCP, metadata proxy, floating IP, all of these are things that are distributed. And another thing that typically the DevOps teams like is the fact that it's a software-only solution. It has no dependencies on any hardware. So they have the ability to do upgrades and manage the software. From the point of view of switching, typically what the switching teams see is, okay, this is just yet another overlay, end-to-end server-to-server flows, and they can manage the networking based on a set of optimizing the performance of traffic flows from server to server. They don't have to understand what are the payloads that exist from the application perspective, which is something I think that's important to be able to separate concerns in operations. OpenContrail also has the ability to connect top-of-rack switches that support OVSDB. This can be interesting when you have, say, a storage appliance and you're providing direct, say, storage connectivity via IP rather than using a block device to the VM. From a perspective of LAN engineering, you have the ability to connect different clusters, and to do that with a technology that most WAN engineers already understand and they have deployed in their networks, which is BGP MPLS. From our perspective of SecOps, you have a scalable implementation of security groups, and you have a way to verify that the traffic matches those security groups. From a perspective of implementation, the way it works is that we build a custom data plane. The vRouter agent performs the forwarding operations and the flow table matching operations. There's a custom message bus for configuration updates, which is translating the Neutron database into this graph database and automatically figuring out which compute nodes need the which configuration objects. And there's a custom message bus for IP routing, which is based on top of BGP MPLS. The other thing that's kind of different if you come from sort of a networking background and network operations is there's no command line interface to the system. Everything is controlled via REST API, and it really looks like a distributed router. It's a bit of a shock if you're coming from the perspective of managing routers or switches. Is very different manageability. And again, if you come from a network background, you can think of a cluster as a single network element. So if you're used to looking at a router, a modern router is typically a distributed system with multiple control engines and then multiple line cards. You can think of a cluster of, say, 10,000 machines as being a single network element. That takes some getting used to. So additional resources. There's a lot of information on the project available on OpenContrail.org. I would encourage you to join our mailing lists, users and dev at listopencontrail.org. There's a wiki available with lots of information on provisioning of the system, and you can always join the OpenContrail channel on ircfreenode.net. I don't know if there's any time for questions.
Yeah, I think we have a few minutes.
A few minutes. Please.
Yeah, if I understood you correctly, you're offering a layer 3 connectivity to the VM. Is that correct?
Layer 3, and we also support non-IP traffic, so we can also do broadcast domain emulation, but most cloud applications only send IP traffic.
If I'm having a legacy workload, like any kind of interconnect, cluster interconnect application, which requires layer 2, is that working as well?
So there's two answers to. So the answer is yes, we support that. So when it's IP packets, it's a layer 3. Although the VM will see subnets, we don't really care about subnets except for multicast. But we also support non-IP traffic. So we have some, especially telecom workloads, they still use some protocols they developed before IP existed, and we support that through VLAN emulation. But yeah, what we called, if it's an IP packet, is our L3 solution. Any additional resources?
So, you did a slide on this load balancer as a service. Is part of OpenContrail?
Yeah.
So, I mean, as far as I understood from the presentation, this load balancer as a service works for HTTP. I mean, you presented the HTTP
Or TCP.
So, does it work for any other protocols like SIGRAN, Meter, SIG, or let's say lower level, UDP, SCTP, and so on?
SCTP, yes. So if you look at the Neutron LBES API, the Neutron LBES API today is defined as supporting HTTP, HTTPS, and TCP. OpenContrail also supports IP Anycast, which is equal cost load balancing of IP endpoints. So that would work for UDP. But that's not what the Neutron LBES API supports. Right. So in the context of this presentation, the assumption here is that you start with a workload description that's using only the Neutron API, and now you're mapping this to a specific Neutron implementation. So when I present the load balancer there, it's in the context of doing the Neutron LBES API. But yeah, we do have extensions that allow you to do Anycast. Thank you very much.